Shafts are commonly used to carry values throughout a computer. One revolution of a shaft is assigned a numerical value. If rotation in one direction is designated as positive, then opposite rotation is negative. The nature of shaft values can be demonstrated with a rack and pinion. In this case, the rack is calibrated, so that one revolution in this direction represents plus 10. Continuing with a half revolution, shaft value now is plus 15. Another half revolution, making a total of 2 revolutions from the 0 position, and shaft value is plus 20. Now add minus 2 by 1/5 turn in the opposite direction. The result, of course, is 18. Similarly, 2 complete revolutions in the minus direction subtract 20. And in this case, the result is minus 2. The rack and pinion were used here to demonstrate the nature of shaft values. In practice, racks and pinions may be used to translate shaft values to corresponding linear movement. Or the rack may transmit values to the shaft. Gears are usually used to transfer values from one shaft to another. With a gear ratio of 1:1, the numerical value remains unchanged, but rotation is reversed. With gears of different sizes, shaft values may be multiplied or divided by a constant. With this gear ratio of 2:1, one revolution of the driving shaft causes 2 revolutions of the driven shaft. Differentials are used in computers to obtain continuously the algebraic sum of 2 quantities. These quantities represent the inputs. As the inputs vary, the differential simultaneously delivers the answer, no matter how rapidly the inputs change. This is a bevel gear differential. There are other types, but we are using this as an example because of its frequent use in fire control computers. To understand how it works, it's necessary to know something about its construction. Remove the gears, and you see 2 shafts. They are solidly joined together. The shafts and these gears form an assembly called the spider. These are the spider gears. This is the spider shaft. And these are end gears. None of these 4 gears is fixed to its shaft. Each gear is freely mounted on bearings as shown in this cutaway. Connections to other mechanisms are made through spur gears. One lock to each end gear and one lock to the spider shaft. Additional gears and shafts complete the connections. Although there are 2 spider gears, only one is needed for the mathematical problem. The other is there to balance the mechanism. So we can remove one spider gear, and we now have the basic elements of a differential. To study its operation, it is necessary to count and compare revolutions of the end gears and the spider shaft. That isn't easy to do. We'll show the differential action in a way that's easier to follow. Essentially, this differential is a gear between 2 gears. Now imagine that you cut the end gears and make them flat. You now have a pinion between two racks. The operating principle is the same as the bevel gear type. Either rack, A or B, or the pinion may be used as the output. The other two parts then are inputs. We'll use the pinion for output, the racks for inputs. Now let's examine the mechanical action. Motion will be plus or minus, measured with reference to the 0 point. Move A 4 inches in a plus direction, and B 2 inches. The sum is 6 inches. Note that the pinion center has moved 3 inches, or half the sum of the rack displacements. When A is at 1 and B at 3, the sum is 4 inches, and the pinion center is at 2 inches. As another example, move A to minus 4 inches, and B to plus 2. The algebraic sum of the rack displacements is minus 2 inches, and the pinion center has moved to minus 1. Measured from 0, the change in the position of pinion center is always half the algebraic sum of the rack displacements. Because of this relation between rack and pinion movements, a differential can be used as a computing mechanism. Instead of inches, we assign a desired scale of values to the racks. Then, with half that scale for the pinion indicates the algebraic sum of the rack values. 3 plus 1 on the racks, 4 on the pinion. Plus 1 and minus 2, minus 1 on the pinion. Plus 3 and minus 3, 0 on the pinion. There is no fundamental difference between the rack and pinion differential and the bevel gear type. The racks, which are limited in length, are replaced by end gears, which serve as endless racks and handle values in the same manner as do shafts. The pinion is replaced by the spider gear. Movement of the spider gear center along its circular path is delivered as rotation of the spider shaft. Adding the second spider gear to balance the mechanism, we now have the complete differential. It should be remembered that the output may be either one of the end gears or the spider shaft. The other two then become the inputs.